Hello, good morning, my dear faculty members and participants from all over India. This is Noor Ahmed, Assistant Professor of Mechanical Engineering Department, Gates Institute of Technology, Coordinator for the 7-day Faculty Development Program on Advancements in Mechanical Engineering. So, hope yesterday everyone had a wonderful session on mechanical projects and publications by Sri Sudhanshu Bandari Garu. After that insightful session, today we are having an informative session on ahead. So now I request Dr. S.L. Prasad sir to introduce today's resource person, Dr. D.V. Ramamurthy Garu, Principal Satyasai Institute of Technology and Management, Vizianagaram, Andhra Pradesh.
A very good morning to one and all. It is my honor to introduce today's speaker, Dr. D.V. Venkateramana Ramamurthy Garu. It is BE in Mechanical Engineering from Andhra University, College of Engineering. He completed his MTech in 1992 from Indian Institute of Technology, Delhi. He did his PhD in Mechanical Engineering in 2005 from Oklahoma State University, United States. He started his career as a lecturer in Kavikulaguru Institute of Technology and Science, Ramtech in 1987. Then he became as assistant professor in 1995 and then taken the charge of HOD of Mechanical Engineering in 1997. He worked as graduate teaching assistant from 2000 to 2004 in Oklahoma State University. And then he joined as research and development mechanical engineering in 2006 in R&D department, Oklahoma City. During his stay, he worked on design, analysis, and testing of new line of pneumatic brakes used in converting corrugating industries. His efforts resulted in 2 novel design patents. He served as principal for Ideal Institute of Technology, Kakinada during 2009 to 2012. And then he worked as professor and dean from September 2012 to May 2015 at Sri Vizianagaram Engineering College, Tirupati. He also served as professor and principal to Godavari Institute of Engineering and Technology, Rajahmundry from 2015 to 2018. Presently, he is working as principal for Satya Institute of Technology and Management, Vizianagaram, Andhra Pradesh. Sir has published more than 25 papers in various national and international journals. He has attended more than 25 conferences held at national and international levels. He conducted more than 20 faculty development programs in various colleges. Coming to his research interests, so logical systems, non-linear dynamic systems, web handling systems, design of mechanical systems, micro, nano mechanical sensing techniques. So now I welcome Dr. D.V. Ramamurthy sir to take over the session and enlighten us with his experience. Thank you, sir.
Good morning, sir. I hope I can share the screen. Is that okay now?
Yes, sir, you can share the screens now, sir.
Okay, I'm trying to do that. I guess you need to give me permission for doing that. I am sharing the screen now. Okay. I hope everyone can see and hear me clearly.
Yes, sir, we are, sir.
Oh, you are hearing very wonderful, excellent, beautiful. Begin by briefly introducing myself. You have heard it, but it may be a good idea to see it. So I briefly list out the details about myself, because only when we know each other we can talk freely. I'm born and brought up in Vizag, in Andhra University campus. Consequently, I did BE Mechanical Engineering from Andhra University, and then MTech from the Indian Institute of Technology, Delhi, and then PhD from Oklahoma State University. And then started Ramtech. That's where I think the teacher in me took shape under the guidance of Kumari Tigari. And then as a part of work experience, I worked with a company called FIFE, F-I-F-E, for 3 years, and then came back to India I worked as research and development mechanical engineer at FDP. And I must say here that I am what I am because of my teachers and my parents. I bow to all of them in reference before I begin. I can definitely say that anything interesting, original, or beautiful that you see in the presentation, pale imitation of all my teachers and my parents. And if you see anything dull, drab, and boring, that is coming from right here. Okay. I once again, because Durga was only 4 days before, I once again bow to all my teachers. Andhra University High School, then AVN College, Rajagaru, Yernan Garu, Padmavati Garu, Fatima Garu, Andhra. And then at Andhra University, Professor NL Rao Garu, P.K. Sharma Garu, E.L. Murthy Garu, all the others. At IIT Delhi, U.P. Agarwal Garu, Atre Garu, Asmani Garu, Gupta Garu. And similarly at Oklahoma State University, Professor Prabhakar Garu, Professor Luca, Professor Yang, Professor Yen, and all the others. It is because of them that I am confidently trying to stand in front of you and talking. Okay. Just one little thought about parents and teachers. This is a little conversation here. Maybe I'll leave it for a second so that you can read it. And in grand old days, we don't used to have 4G or 5G or something. We used to have only 3G. And those 3Gs are living, talking, teaching, mentoring, Mataji, Pitaji, and Guruji. And whenever we did something wrong, we get a good hard slap, and all the whole universe comes into our view. That's how we get our knowledge. And in this week of Guru Purnima, once again, I bow to all the teachers, including my parents. And I try to begin what I have to say. This lecture, I thank Patil Bhaskar Garu and Selvi Prasad Garu and the whole team at Gates Institute. They're all nice, wonderful, excellent people. Patil Bhaskar Garu is multifaceted, Bahumukha Pragyasali. I really thank him for this opportunity of sharing whatever little that I know in this area. And in fact, this is the second webinar of the same type, exactly a similar one I did with Geetanjali College in Hyderabad, and then started the trend. And this is the second time I'm talking about Solidworks. I'll try to make it short, sweet, and painless, as short, as sweet, and as painless that I can make. Okay. Maybe it may take about 35, 40, 45 minutes, and then maybe 15 minutes if you have questions, and if I can answer, we'll have a question answer session, and then close the presentation today. Okay. This I titled it as a bird's eye view of SolidWorks. Just an overview. I'll try to be the SolidWorks salesman here, and try to give all the features of SolidWorks in a nutshell. Okay, it's not possible to go through all the features of SolidWorks in any sense of the word. So I'll try to do a little bit of introduction, and then try to go and present about SolidWorks. In this, I won't be showing many details, but the overall philosophy and the way the world is going with paradigm shift from 3D to 3D. Okay? The AutoCAD originally started, they started with 2D drawings. That is, we think in our brain in 3D and put the drawing in 2D. The other person who receives our drawing will look at it in 2D and think in 3D. So there is seeing and thinking difference. That difference is what is built up by 3D packages. For example, it took the Autodesk about 10 years to go from 2D drawings into a 3D paradigm. We briefly see what this 3D paradigm does for us, how we can use it. Basically, maybe I'll see only two features, main features, activity enhancers. One is what we mean by configurations, and another is what we mean by design equations, how we use them to increase the productivity. Okay. With that said, I only would like to consider myself as a little bird flying around and trying to see what it sees. Let me go through to the next slide, okay, wherein I'll try to present the production cycle as I have seen. I worked for some time in thermal area and then in control systems area, and then I came into production cycle. So my view of production cycle is rather simplistic, and it begins with designer, a smart young boy, thinking in terms of 3D. You know, when you actually build a mechanical product, you think in 3D, and then you try to translate it into I think something went wrong here, but I guess it's okay. And then this drawing generally goes in the form of 2D drawings. For example, you design something, you make a 2D drawing and then send it to the shop floor. When you send it to the shop floor person is a production manager or maybe a supervisor.
Sorry to interrupt you, sir. Sorry to interrupt you, sir. Actually, screen sharing is off, sir. Actually,
Sir,
the screen is not being shared, sir.
Screen is not being shared. Okay, I don't know why it.
You just again share screen again, sir.
Oh, okay. I'll share the screen again. That's what I'll do. That's what I'm doing. I really apologize for that little hiccup. Okay, I need to go to this and then share the screen. I don't know how it came out. Maybe by mistake I clicked on something and it happened. Okay. Now is it clear?
Yes, sir. It is clear, sir.
It is clear. Okay. I'll just rewind a little bit and try to go through what I have been doing. The designer, the original one who conceives an idea and then puts it across for production, he thinks in 3D in terms of objects that have all the three-dimensional features. But when he sends it, he has it across as a 2D drawing, you know, like lines, curves, and points that can be shown on a piece of paper. And when once the production manager receives, and he again thinks in 3D, and he has to conceive what is written in 2D into 3D, and then pass it on to machinist in the form of the same drawing that he receives here, okay, which is again 2D. The machinist produces the product and he sends it to quality control person, and this time around he sends it in 3D. So the three key people are talking and thinking in terms of 3D, and yet there is a conversion going on in between, from 3D to 2D, from 2D to 3D, from 3D to 2D, again 2D to 3D. So the quality control guy checks this and gives a feedback to the designer, and the whole cycle goes on. I don't know whether you call it a design cycle or whether you call it a production cycle, but it's a cyclical process involving thinking in 3D, showing in 2D, seeing in 2D, thinking in 3D, then seeing in 2D, producing a 3D component, and then verifying the 3D component. This guy is lucky. He gets everything in three-dimensional and full detail. This guy kind of is lucky because whatever is his idea that he has in his brain is coming into 3D. So this cycle perhaps is a little less intuitive and more time consuming. For example, what if this designer can think mechanisms but cannot make a drawing? Or what if this excellent production manager cannot convert from 2 dimensions to isometric view? What about this production guy? What if he cannot read these drawings? They all will be handicapped in certain sense because they don't have the object in their hands. Okay? Essentially, what we need is right from the designer all the way up to the quality control guy, if they can see the object that they are dealing with right in their hand, as easily as we hold this hand, something like this, if you can hold every object, that would be wonderful. Such a gap is filled by all the 3D packages. Okay, when you have the paradigm shift from 2D to 3D, this is what it will be. It won't be drastically different. It will be mostly the same because 2D drawings are a must. Whenever you sign a contract, you need to sign it on a document. On that document, you need to have all the details. Such details can be shown in 2D drawings. So when the designer thinks in 3D, makes a 3D component, kind of holds it in his hand and sees it on the screen, and then makes a the 3D drawing is very easy. You click in the click of a button, it will show 2D drawing. And then this product manager, he thinks in 3D, he sees 3D. And then communication, and then the communication to the machinist is again in 2D and 3D. And then machinist can see the 3D drawings, can see the actual product. So the cycle is more seamless. Okay? All the people, they know what they are thinking, they know what others are thinking, and they can see what they are seeing on the paper in actual screen. Such a paradigm shift already occurred. In fact, it occurred maybe several years ago, maybe some 9-10 years ago. It has caught up very beautifully in India, thanks to the widespread use of packages like, the Inventor, then Solid Edge, and Solidworks. Long time ago, I was involved in a study on estimating costs of products made in 5 countries: Brazil, Russia, India, China, DRIC, maybe Korea. Okay, the so-called BRIC countries, DRIC countries. And as a part of that, I roamed for some time in Kenya industrial area in Hyderabad. In effect, I was trying to estimate the cost of a aluminum die cast component, and I was amazed at the speed. I walked into a small shop in Hyderabad, and the moment I gave him the drawings, SolidWorks drawings on a zip drive, he quickly imported, and then he calculated the volume, he estimated the cost, everything within 10-15 minutes. Such fast response is possible when we use this high-end software. I'll try to only walk through the bare minimum thing, whatever little I knew about it. As a design engineer, I used to make such drawings with GD, and all. Whatever little I gathered there, I will try to share it in a short time, in a sweet way, and in perhaps painless way. Okay? Now that we saw that a 3D package is useful, we need to know how we go about making a drawing in 2D. It involves one kind of workflow. Making a solid visible in all its dimensions in isometric view is another. So typically, when you try to use any three-dimensional package to generate assemblies or to generate solids, and then produce drawings, typically the end product of that is a 2D drawing, because anybody has to sign a contract for manufacturing, that has to be on a paper. So it basically better be a 2D drawing. Okay? Even the most complicated assembly begins with a sketch on a plane. Okay. Then typically we make it a constrained sketch. Constrained sketch, we will see what it is. The constrained sketch is a fully defined sketch. Okay. There is nothing left to be designed. Then you make a constrained sketch, and then you design a devise a feature. This feature is where the object gets its three-dimensional shape, and then you keep adding many features as you want to get a solid. Okay, so this sketch, constraint sketch, series of features is what defines a solid. And once you have solid, you can have several such sequences to devise several solids. For example, you follow through sketch 1, constraint sketch 1, feature 1, feature 2, solid 1. You follow the same features to define another solid. This solid resides in one file. This solid resides in one file. You bring all of them together to make a small assembly. Okay? That we call a sub-assembly. This sub-assembly, along with several sub-assemblies and the solids we make, they form a assembly. And once this assembly is made, then you can decide some features. They call it assembly features. These are solid features. This is assembly feature. This assembly feature may involve putting in a small nut hole, tapping a little hole and putting a nut there, or putting a sticker there, or painting it, or sending it into particle bath, or cleaning it, and things like that. Those things, they can be called assembly feature. And once all the things is complete, the product is ready to be shipped, put in a box, you call it final assembly. And once the final assembly is done, you put it on a drawing always and store it in the art library. Okay? So this is the whole workflow of a typical three-dimensional drawing package. Okay? Solidworks also follows this kind of feature, but the beauty of Solidworks is you can start at any point and travel in any direction. Okay, you can start here at final assembly. In the final assembly mode, you can start doing the part. Halfway through designing the part, you can insert assembly, and then final assembly, and then go here. So the workflow differs from person to person. Typically, I think simple with my simple brain. I start with a sketch, then follow this to create a solid, and then create another solid, then go through this part linearly, like a snake crawling on the floor. We go through all these things. It may not be possible to show all these. For example, you have what you call, whenever you say sketch, you need to define a plane. A plane is a reference geometry in terms of SolidWorks. They are gone. You need to devise several planes. 3 planes are already given for you, front, top, and right plane. Then you need to define what we mean by mates when two solids come together, how do they fuse? How do they fit in together? Is what is called a mate in SolidWorks. Similarly, when there are two subassemblies, you have mates here and then mates there, and so on. And going from here to here, you will have what are called constraints. Constraints either are conditions or they stand as dimensions. Okay. With this, what I'll try to do is I'll try to show a few simple things. How do you draw a cube? A cube is a flat, is an object made out of several flat surfaces, plane surfaces, and then I'll show one sphere. Sphere is a surface that is generated by revolving, and then these two, in fact, I will show through one example. Okay. With this, I think I will go from here to I will open the SolidWorks package and then show all these things. I think I need to stop sharing this to shift from this to SolidWorks. I'm stopping the sharing for a second. There'll be small cessation in presentation, and then I share the whole screen. Oops, I think I need to come out of it. Okay. Okay. I'll close the presentation here and then start the SolidWorks thing. Okay. Can you see the screen, sir, now?
Yes, sir. We are seeing the screen, sir.
You are seeing the screen. Wonderful, excellent, beautiful. Okay. Okay. This is how your SolidWorks startup screen looks like. Okay. SolidWorks 2003 or 17 or menu changes and a few efficiency tips and tricks. The SolidWorks package more or less this and represented as icons here. This is for a new part, this is for open, and so on. Okay, and let us say we want to create a new thing. Okay, in SolidWorks you can create three distinct entities. One is a single part, that is a solid. Second is an assembly, when you put two or more solids into one place and kind of stitch them together using mates. The third is a drawing showing top view, front view, and side view. Let us begin with a simple part, because that's what we said forms the basic unit. And then this we say again is a part where you generate parts. Okay, we said our first entity in the video, when you try to draw it in SolidWorks, is a sketch. So somewhere look on the screen and find where sketch is. And fortunately, I could find it very quickly here. The sketch is here. And then you need to start a sketch. When I say a sketch always happens on a plane. SolidWorks has three defined planes. The three defined planes are the front plane. The second one is this top plane. The third one is this right plane. And the moment I saw this, I was really fascinated, because when we draw any solid on a drawing sheet, part of our engineering drawing class, we see only one line that shows above and below. Okay, the moment you see this, you realize that your coordinate planes break the whole space into 8 quadrants, and you can place an object anywhere and view it from any angle. Okay, this is very useful when you are teaching engineering drawing. Engineering drawing and 2D drawings are very essential, but if you show such a setup, it's very convenient, and it helps people visualize first angle, third angle, and all the others. Okay, you can choose any plane to begin with and make a sketch. I always choose the top plane, not that I want to be on the top, but somehow or the other I'm down, and so I want it to be something like this. These show 2 coordinate axes. If you call this as y-axis and this as z-axis, your x-axis is coming out of the screen towards you. Okay? I'll try to make one simple object. As we discussed, I'll try to make a cube, and you can kind of see how quick it is, how easily people can visualize. Okay, there are several drawing tools here. Okay, and there are several cutting tools here, and there are several visual tools here. Okay, those are 3 areas. Okay. These 3 are this little box here. This little box here gives us several entities, and one such entity is a rectangle. Okay, I will take a rectangle here and then kind of draw it. Okay, you can notice that this rectangle has a blue edge. Okay, in the solid edge, I configured it. A blue edge is an unconstrained edge. Okay, a blue edge is a sad edge. It doesn't have constrained sizes and limitations placed on it. Somehow or the other, we need to make that constraint. I'll try to do that and kind of show you. This is a roundabout way of doing. The way I do is I will draw a diagonal here. Okay, and you can start with lines. Okay, this is a construction line. Okay, construction line. What I'll do is I'll kind of try to move my mouse around. When I try to move my mouse around slowly, Solidworks at the back of his mind thinks that I'm searching for some important point. An important point is the center point. Okay, I click on the center point, and then I click on this point. Okay, selected both, I can put a constraint. The constraint I want to place is that of them are coincident. That is, I want to start drawing the rectangle in such a way that center of the rectangle is at the origin. The moment I choose this, you see the rectangle moved, so that its center lies at the origin. This is a roundabout way of doing. I have done this only to show that you can put constraints like that. You can have certain points locate in a certain relative position with respect to origin. But actually, we won't do it that way. We will actually, if at all that is what we want to do, we will see the center rectangle here, then locate this center and draw it. It nicely draws both the diagonals and construction lines, coincides the point of intersection of the diagonals at the origin, so that the center of the rectangle is fixed at the origin. Origin is a fixed point for all the geometry that we are going to build. Once we do that, we see that still the lines are blue. That means it is not defined well enough to seriously qualify for a solid. Of course, Solidworks won't complain if you go ahead and make a solid out of this sketch, but it's a good idea to have it constrained. One way of making the constraint perhaps is putting a dimension. Chosen one part, and let us say I choose 50 millimeters, 50 mm. Other units are possible. I guess you can click on it and you can change the units. Units are somewhere on this side of the box. You see the unit. If you scroll down, I'm leaving it there. It is enough if we know that we can change the unit. Okay. The moment we do that, you notice something. This edge and this edge, they turned black. Black, in some sense, indicates that either relative position or relative size is defined. Their relative position is defined. They are 40 millimeters away. We need to make these two lines also black to make it completely constrained. Either you put a dimension or you put a constraint. Okay, I'll try to put a constraint here. I'll say that this side, I'll hold the control down and click this side. These two sides, I would say, that are equal. And now you see everything turns black. Okay, that means the whole sketch is constrained now. And these lines, they indicate construction lines. Okay, so this is 40 millimeters. This is also 40 millimeters. Both are equal. Once you have the sketch completely in black and in a shape that you want it, your sketch is complete. Either you can exit the sketch here or you can exit the sketch here. Somehow I prefer to do here. Once you do this, you are through with step 1. Hello, can you hear me, sir?
Yes, sir. We can hear you, sir.
Wonderful. You can see also?
Yes, sir. We are able to see, sir.
Okay, wonderful. Somehow power went off here and I got it out. If there is a break in communication, call me at the phone number and inform me. Otherwise, I don't want to be talking to myself in the event of a communication gap. Okay, I would request Selvi Prasad Garu to make a call to me, because I don't see anything on the screen to say that audience is looking at me. Okay, that kind of feedback I would request Selvi Prasad Garu to kindly provide it to me. I'll trouble. Now the sketch is completely made. Okay, this sketch somehow or the other you can convert it into feature. We have seen the workflow is a sketch, a constraint sketch, and then a feature upon feature upon feature that will define a solid. We'll try to see one very simple, extremely simple feature. Okay, there are several features here. This is extruded boss. It requires only one sketch. Revolve, it requires 2 sketches. The sweep, it requires 3 sketches. Loft, it requires 2 sketches, and so on. The simplest of all these features is an extruded boss, an extrusion. Okay, the moment I click it, because there is only one sketch, it understood which is the sketch that it needs to use and kind of trying to show it. You can hold on to it and you can move up and down, okay, to see what is the size that you want to achieve. There is a scale provided over here for us. Enter the dimension here, because we said we are making this cube. We'll take the dimension to be 50 and then close. Once you do that, this object is here. You can bring the whole object into the screen by different ways. So you have this cube. You can see all the angles of it. You can see the father of this cube. The father of this cube is the sketch, and that is what is being shown there. Okay, you can see the father of this cube and the whole family of entities within this cube. This cube has I think 6 faces, four faces. Four faces are these four faces: 1, 2, 3, and 4. Four side walls and one top and one bottom. Okay, this is the whole cube. And in fact, this is one feature. Okay, one feature is one 3D operation that you do on a sketch. Once you have this solid, you can have several other features built onto it. You can choose any one plane and say sketch. Okay, the sketch comes in, and most often I would like to see it normal to it. So this came in, and we can have several other features. For example, I take this center point arc. Okay, and let us say I draw the center point. This is the center point, and the arc is drawn something like this. Okay, you can do that. Let me try to do that. The center point arc as chosen, and I choose the center here, and then I draw the arc. Okay. Somehow it is hanging up. Maybe I'll try to do something. Maybe I'll try to do something different. I'll show you one more operation. One more operation would be, let us say you want to cut a rectangle out of here. I will choose a rectangle. I will start from somewhere here and draw a rectangle. I'll choose corner rectangle. Start at this corner, and then choose this, and maybe I can give a dimension, a little bit of a dimension. Let us say 10 mm here, and I can further constrain this side and this side being equal. Okay, whatever it is. When you do that, this whole thing became black again. You can see this is black, this should be black. And once that is done, our operations are done. Now you see there is another little box open with several other features. These are secondary features. These are primary features because they create an object. These, they modify the existing object. Of course, everything modifies the object, but these operations cannot create an object. For example, let us say I want to do an extrude cut. Okay, and I can do that with several options: through all, through both, up to next, and so on. I'll cut through all and click OK. You can see that. You can see that one object is generated. Once an object is generated, these are tertiary options available. Okay, for example, a linear pattern. Okay, let us say we choose a linear pattern. We choose direction one as this, and then we can choose direction two as this, and then we can choose the featured areas and faces. You can choose this feature. The features are here. You can choose this cut. Okay, and you can click OK. I'm doing something crazy. Okay, it added the material back into it. Okay? I'm just showing these just for fun. So this creates one solid. You can create several such solids, and perhaps you can join them together in meaningful ways to create what is called a subassembly. From a subassembly, you can create a bigger assembly. From a bigger assembly, you can draw a section. From the section, you can show a 3D drawing. Okay, I won't do all that primarily because I'm not so conversant that in a conversational setting I can show it here. But instead, what I'll do is I'll show two productivity features, three features that are very useful for SolidWorks guys. Those two features are: one, a design equation; two is a configuration table. We call it design table in the context of SolidWorks. Okay? Let me try to show what I mean. By this. Let me open a picture and let us say it is. Okay. This shows, you can see a family of parts. Okay? I've shown only 3, but in fact there could be 30, there could be 100 parts. Okay? In a typical industry, even if it's a very small industry, I worked in a very small industry where there are only 50 employees, but still the number of parts that are handled sometimes could be more than 20 lakhs, 30 lakhs, because there are several wrenches. Wrenches come in 100 sizes, so they become 100 parts. You get bolts and nuts. There'll be hundreds and hundreds of sizes, both ANSI bolts and millimeter bolts. You could have a stud, you could have plates, you could have retaining plates. Many of them, they share common features. Objects that share common feature, they are called a family of parts. These 3 components, they fall into one such family. All of them are built with plane faces. All of them are rectangular parallelepipeds, but with different sizes. Some of them can have a hole here, some of them can have a hole here, and so on. So this family of parts that share several common features, but with small exceptions here and there, those can be handled very well in SolidWorks. In one go, you can create a whole family. Okay? Let us try to see how we do that. Okay, I will perhaps close it here and start a new part altogether and try to show and close this also. Now that we are done with it, I don't even want to save it. I start a fresh part. Okay, part of it looks exactly similar to what we have done, so I'll kind of try to do it real quick. I'll choose the top plane, and then I'll choose the center rectangle. Rectangle center is chosen there, and something like this. Okay. And I give dimension to one side. Okay, it is here that the trick lies in. Let us say that I have several such plates, several such plates. One has a 100 meters length, 100 millimeters length, another has 200, another has 300, the fourth one has 150, and so on. We want to be able to capture all that in one part. We do it once, but you have different components. Okay, that is the kind of setup we are trying to look at. Because if we do that, we'll be able to represent a whole family of parts with one drawing. Okay. And I will try to put the other dimension just for the sake of illustration. Let us say I put it at 50. Okay, then I give both the dimensions. The stage became constraint, which is entirely black. I will close it, and then I choose features and I extrude it, and I choose it as 25 mm. Okay. Now there is one part here. Okay, from here the real fun and productivity begins. Okay, once you have this, okay, you go to this annotation and say show feature dimensions. See what it did. It kind of showed the dimensions of the parts. Okay, maybe I need to move it slightly this way. Okay, to see the dimensions, all the three. Okay, alongside you have one other feature, that little eye there, that either sees or touches eye on several things, and you click the dimension. Okay, it showed its internal names given to these dimensions. Okay, D1, D2, whatever is the dimension D1. These be confusing. This D1 and this D1, we may get confused. Okay, so what we will try to do is we'll try to give a name to this. We'll understand why we are giving this name in a little while. Okay, if I hold it slightly, move it here and there, and leave it. Okay, some box came in here. It has a name, so I can safely give it a name, length. Okay, you can see that the name length came in here, and I can move this a little and leave it. Something came here, I can call it breadth. Similarly, I can move this a little bit and leave it. This is thickness. Okay, so you can not only define solid, but give meaningful names to it, so that you can later refer to them in creating other complex objects. Okay, once we did that, we can do something really nice. Okay, for example, I come here and double click on it. If I double click on it, I get this little window. I come here and say is equal to this dimension. I click on this length divided by 2. Okay, and then I can double click on this. It will bring this, and I would say is equal to this divided by 2. Okay, so this part now creates one whole family of parts. Okay, family of parts that have a length of 100, a width half of the length, and a thickness half of the breadth. This defines this. Now we have a scope of defining several solids. Such solids. You may have a solid 100 mm solid where the length is 100, a 120 mm solid has a length of 120, and so on. If you specify just one number, okay, all the other features of the solid are separated. Of course, that will not be the case generally. You may have to define 4 or 5 parameters to define a solid. But for this 45 minutes presentation, I took a really simple solid that can be defined with one dimension. Okay, this 100. This 100 drives everything else. Okay. In more difficult situations, you may have 2 or 3 such driving dimensions. Okay, which will kind of define the object in all its possible shapes. Now Solidworks nicely puts this red sigma. I have a red sigma here. I have a red sigma here to let us know that that these are driven dimensions. I hope it is clear so far, Sir Prasad Garu.
Yes, sir.
Okay, and I'm trying to confirm whether you are able to listen to me and see the screen or not. You are able to see the screen, right?
Sir, we are okay, sir.
Okay, wonderful. This is all one side, beautiful. You can do something more from it. Okay, let me try to reduce the size and pull it to one corner here. I'll pull it to one corner here because I want to have a bit of space around here. I'll pull it to one corner in such a way that I'm still able to see the 3 dimensions. The other excellent feature of the Solidworks, a productivity enhancer, is in terms of what we call tables. You can go in to insert and then insert a table. There are several types of tables. Of that we are interested in is a design table. Okay, a design table. I chose a design table, and it gives me several options. Okay, for this presentation again, I don't want to go into auto create or from file. I will try to start with blank. Okay, with a blank table. Okay, it kind of complains a little bit because we didn't start defining a table yet. We didn't choose a configuration yet, but we started it. So we'll just say okay, and it opened Excel as an inset into SolidWorks. Okay, SolidWorks is calling Excel and kind of putting it there. Now you can put in our dimensions into Excel. Okay, to put dimensions, we simply go to the sketch here and click on it. You see it. It imported that into Excel there, and it created a part. The part name it automatically give as first instance, but I can change it as part A. Okay, part A has 100 mm length. I can define several other parts: part C, part E, part E, part F, and so on, and give their dimensions. This default is one which we should not change it. Just leave it as it is. Let us say this default is very big, 500. This B is 200. This C is maybe I go in small steps. 120, 140, 160, and then 180, and then 200. Okay, I've defined all the parts. So with this table, in a way, we created 5 parts. All the 5 parts share the same sketch and same feature, but with different dimensions. Okay. Actually, you don't have to use an equation to define half of it. You can have breadth as one column heading here, height as one column heading here, and input the values. I'm kind of lazy in typing, so I am leaving all those there. Once you do that, you can come out of this Excel. I came out of Excel by clicking anywhere, and it is doing its computation inside, and it generated these configurations A, B, C, D, E, F, and I say okay. Okay. Since most of my part is done, I will kind of close the visibility in a minute. Okay. Okay. But I just wanted to show you where these dimensions appear. Okay. There is one tab here that shows configuration manager. There is an appearance manager. There is a dimensional expert manager. This would be very useful when you try to do tolerancing and things like that. There is one configuration manager, and there is property manager. Okay. For a part, you have several managers here. Just like in a company, you may have different kinds of managers. You have several managers here. The manager that we are interested in is configuration manager. Okay. You click on it, and you see all these configurations, 6 configurations. Let me try to click on this and show it. This is 100 mm configuration A. If I click on this, it should 120 mm, another slightly bigger part. And this is even bigger part here. Okay, the B is much more bigger. Okay, 160. Similarly, this F is perhaps the biggest. Okay, so all these different sizes of parts, they are they are put into one single drawing. You can call upon this part and say, okay, take this shape now. I want you to be a length of 200, and take that shape 200. Once this is done, let us say I save it. I save it into, let us say I have something for part 1, I will overwrite it. Okay, the usual dialog, this is done. Now let us say I want to make a drawing in which I use a plate that is having 100 mm length, a plate that is having 120, and a plate that is having 240. How do we do that? It's very kind of easy. Let us say I choose this assembly. Okay, and in assembly you can insert a part. Okay, take the part and leave it here. Okay, this is one part, and I will do the part 3 times in here. Insert component and this assembly, and then a part. I left the second part here. It looks exactly identical to the first one, but we can change that very easily. Okay. Okay, we have 3 parts here. I'll bring them up in isometric view here, fit to size. I can go to each one and say configure. I go to the first one and say configure and choose A. Okay. Okay, it took the shape of A. And I go to the second one and say configure and say, let us say we want B. Okay, it became next bigger size. And again configure and choose C. Okay, now you have 3 different, they appear to be 3 different parts. In fact, you can make them appear totally different things by having different kinds of features that are built into each configuration. Okay. Now comes the another question. What if the smaller one has holes, the bigger 2, B and C configurations do not have that hole? How to do that? That is how to apply specific features to specific configurations. That we can do. Let me save this as a part. Save this as an assembly. Some assembly will I overwrite it, and I go to my part. Okay, part here. Okay, you can see that this one solid took 3 different forms. It is cloning and sizing. Thank God, Corona could not do it. It's not sizing bigger or smaller. Maybe if Corona becomes much bigger and it can be held in hand, Chinese people would have eaten it. Now, maybe that's the reason why it is not getting any bigger. Now that we are done with the dimensions, I'll go here and close that. So I can merely see this. Suppose I want to have a hole. Okay, I can choose a sketch and then look on to the sketch, and I'll draw a random circle. A small circle, maybe 10 mm diameter. See, it is blue now. The moment I apply dimension, it becomes black. Let us say 15 mm. Okay. We come out of the sketch and then choose a feature, a cut, and I will make it do all and close. So that kind of created a hole. You can see that this package is really intuitive. That is what I like about it. Intuitive, It is intelligent and adaptive in some sense. Adaptive in the sense that you can have what are called adaptive features, features that kind of pick up, inherit properties from other solids. Okay? And this is one feature. Now, I want this feature to be visible only in certain configurations. I can configure the feature. Okay, I can suppress it in B, C, D, E, F, and the default one. Okay, and I say okay. Okay, except for one, let us say A. It is not suppressed, in all the others it is suppressed. Okay, use this. So only in A configuration A you see the hole, in others you don't see the hole. Okay, and then you save it, and then you go to your okay. Only in this you see the hole, in others you don't see the hole. So if you have a whole family, okay, whole family of parts which are very similar to each other, but they have few exceptional features here and there. Okay, in such cases you can use the SolidWorks. And now that we said we can do something about assembly, let us say we want to make an assembly out of these three parts. We want to stack them in a certain way. Okay, to do that we need to define what we call mates, how they mate with each other. Let us say I choose that one surface, and then choose this other surface, and then say that they are coincident. Okay. Now both of them, they are touching. You can see that. Okay. Both the bottom surface of this and top surface of this, they are mating. I can further choose this surface and perhaps this surface, then this surface. I don't know whether it works. Okay, and then this space, and then choose what is called a width constraint. See what happens. Okay, this one came in the center of the bigger block, and I can do one more width constraint, something like this, and this, and this, and then do another width constraint. Maybe I can do it like this. I can choose this and this, and then say both these are coincident. I'll do the same thing with this real quick and close the presentation. Both these are, let us say, coincident, and then front faces, they are coincident. Okay. This kind of looks like a stack of books. A stack of books stacked in the wall. And all these weights, you can nicely see the way you oriented them right here. Okay. I think I will stop here to leave maybe 10 minutes of time for whatever your comments, questions, suggestions, things like that. Typically, such presentation should not exceed maybe 30, 40 minutes, because the average span of attention in listening and seeing for an average Asian person from Asia is maybe about 17 minutes, 17. Okay, we can stretch it to 20 minutes, but if you stretch it to 1 hour and beyond, one gets really bored. So I think I will stop here, Prasad Garu. Permit me. I will kind of stop here and leave the floor to you.
Yes, sir. Thank you for the wonderful session, sir. So all the participants are requested to post your queries in the live chat box on the YouTube, and your queries shall be answered by Dr. D.V. Ramamurthy, sir.
Can I stop sharing the screen now, sir?
Yes, sir. You can stop the screen sharing, sir. Yes, sir.
Okay. This Gates PC and Gates Institute, I cannot see any one of them.
Hello.
Yes.
Good afternoon, sir. A few questions are asked in YouTube chat box from the participants. I'll ask
Oh, wonderful.
the questions, sir, one by one. Sir, the question is, good morning, sir. With Solidworks software, can we connect the CNC machines? Is it generate CNC program?
There is an add-on pack I remember, which is called SolidCam. The SolidCam, I don't know whether it can drive a machine or not, but it can simulate machining process and show you. I'm sure there are such features available for components which are relatively very simple. For components that have many features in it, generally people don't leave it for a machine, for a software to machine it. Yes, so your answer is yes and no. Yes, because there is a SolidCam and there is a simulation of machining thing. But generating actual part code, it is possible, but definitely requires a human intervention. A human has to verify. You cannot leave everything to a piece of software. Generally, people don't do that. At least I won't do that. I hope I answered that question.
Yes, sir. Yes, sir. Sir, next question, sir. Can we do critical meshing in SolidWorks, or do we need to go for NXCAD?
SolidWorks comes with a SEM module. I think that is called Cosmos, COSMOS. That comes in as an add-on onto the SolidWorks. If you purchase that also, it will appear as a little tab on the menu of the SolidWorks. You can click on it and then you can do all the operations seamlessly. So the answer is yes, we can have a SEM package overlaid on the top of the SolidWorks. If you want to buy others, you need to export the solid maybe as a step file or as an STL file or as I don't know, some packages they can take directly SolidWorks part or SolidWorks assembly and do a finite element meshing on it. But somehow I would like Cosmos. Cosmos is there. You can very easily do finite element analysis. You don't have to leave the SolidWorks package. You can stay in the SolidWorks package and do all the finite elements within it.
Okay, sir.
Cosmos is the way to go.
Yes. Sir, next question, sir. Does it possible to do modeling of combustion chamber with SolidWorks when compared to the CATIA or Pro-E, so like that? Any easiest process?
I didn't get.
Sir, once again I'll repeat, sir. Sorry. Does it possible to modeling of combustion chamber, some complex assemblies in SolidWorks when compared to the CATIA or Pro-E or some other softwares?
I think CATIA and SolidWorks, they come from the same parent, Dassault Systems, DS. Both are very flexible. In fact, at one time while I was working in industry, we wanted to go for a 3D package, and three of us were engineers. We were asked to evaluate. So we took a Solid Edge, then Inventor, then Ideas, and then CATIA, and then SolidWorks. We took trial versions of these 5 and used for 5 months, each one for a month, and tried to see how we feel. All the three of us maybe that's a strange coincidence. All the three of us felt SolidWorks is the best for it. Though other packages may have lot of flexibility, lot of potential. For example, some people told me that if you use in an assembly, if you use SolidWorks to handle more than 300 or 400 parts, something like 1,000 parts, an assembly with 1,000 parts. They say SolidWorks fumbles, you know. Sometimes it may place the component at a place where it should not be there. And however many times you move it, it goes into the wrong position, or it doesn't show up in the drawing, or the mates disappear, or the system gets very slow with 1,000 components or so. Whereas CATIA, ProE, Solid Edge, I didn't experiment with this. They seamlessly handle large number of parts. For example, they say you can take a whole aircraft. If you try to model it, there may be about something like 11,000, 12,000 individual parts, leaving the bolts and nuts. It can seamlessly handle. I never did more than 60, 70, 80 components assemblies. I never crossed that 100 line. I don't know. But till then, SolidWorks really works beautifully. If you render it, you can create the sculpture of a human being. The Shelby Prasad Gari physics, where we can create a SolidWorks model that looks exactly like a person. But I don't know. All of them cost more or less the same. All of them have more or less the same features. But one feature that is really excellent in SolidWorks is configurations and its adaptive features. Okay, for example, I worked on brakes, pneumatic disc brakes for quite some time. We used to have brakes of different sizes: 250 mm, 380 mm, 470 mm, and so on, in several individual sizes. Okay, it's really very difficult to generate so many drawings for each brake. It used to have 57 parts in it, so 57 multiplied by 3, 170 parts or so, which is very tedious. So we use this configuration and adaptive featuring. Adaptive means in a smaller part, if you have a smaller hole, in a bigger part, you should have a bigger hole. So you can set up the parts in such a way that they fit adaptively. So it is for that feature that we wanted SolidWorks, but all the other packages, they also have similar features, these configurations, adaptive features, and product lifecycle management feature. You can very easily integrate in SolidWorks intuitively, at least as a human would do. That's the reason why I chose SolidWorks. I hope I answered that question.
Yes, yes, sir. Sir, one last question, sir. With using SolidWorks software, can we do the analysis? It's like ANSYS or Hypermesh, like that.
Yes, you can do that. In fact, as I said, you can purchase Cosmos SEM license, and that nicely fits into the SolidWorks. So once you start SolidWorks and draw a part, you don't have to leave SolidWorks to do finite element analysis. You will see a small icon on the SolidWorks menu. You can click on it and automatically analysis begins. Not only finite element analysis, several simple strength of material calculations, like what is the stress at a given point on the solid. How does the bending moment diagram look for a given load? How does the shear force look for a given load? If the member involves a curved bar, how can you do stress analysis on it? Such simple things are also built into SolidWorks. A limited amount of analysis of single parts and interference analysis. Several parts in an assembly have different tolerances will these tolerances cause some kind of malfunction wherein one component penetrates into the other, such a thing is happening or not? Such analysis you can do. So inherently in SolidWorks, you have certain analysis things built in. Whereas if you want extensive finite element analysis, you need to buy either Cosmos or Console or ANSYS, or if it involves fluid things, you can buy Fluent. Of course, now a couple of years ago, Fluent is purchased by ANSYS. So if you buy ANSYS, you can do all the kinds of things. You can import this SolidWorks model into ANSYS and perform the analysis. I hope I answered the question.
Yes, sir. Thank you, sir. Thank you very much. Now it is the time for vote of thanks, sir. I request Dr. S.R.V. Prasad, sir, to propose vote of thanks.
So on behalf of Department of Mechanical Engineering, GATE Institute of Technology and participants, I, S.L.V. Prasad, great honor and privilege to thank the speaker, Sri D.V. Ramamurthy, sir, all the valuable information shared with us today. So thank you, sir. Thank you very much. And I thank all the participants who have given their valuable time to attend the session. Thank you. Thank you very much.
Thank you, sir. You can close the session now, or I can leave, right?
Yes. Thank you, sir.
I leave the session.
Yes.
Can I leave the session, sir?
Yes, sir. Yes, sir. Yes, sir. Yes, sir.
Okay, I'm leaving in the count of 5, 5, 4, 3, 2, 1, 0.
Yes. Thank you, sir. So, and I thank all the participants who have given their valuable time to attend the session. Thank you. Thank you, everyone. Thank you very much. We are sharing the feedback link in YouTube chat, live chat. So all of you, please send your feedback.